So where we left off last Thursday, I was in your book, and I'm on page 396, and we were looking at p-values and test statistics. So I'm going to do it like this: the test statistic and p-values. They go together. And where I was looking at is I was looking on page 396, there's a little box there. It says test statistic and p-values. And I had talked about this test statistic is calculated from the sample data. It's calculated from your x-bar. And I kept telling you, your test statistic, that's nothing more than a z-score. All right? Measures how far the data diverge from what we'd expect if the null hypothesis H0 were true. Look, I told you on Thursday that H0, whatever that is always mu is equal to. Right? So it's telling you where that sampling distribution is centered. So this test statistic is telling you how far out the tail your x-bar is. Right? How far away from that center it is. Again, your test statistic, as simple as I can make it, it's a z-score that we've already calculated. We know how to do that. That's nothing more than a z-score. Okay? Now the big thing about this is the last little part there about a test statistic. Large values of the statistic shows that the data are not consistent with H0. Large z-scores are telling you that your x-bar is really far out the tail. Large values of your test statistic is telling you there's something up here that where you've claimed that the sampling distribution is centered, that value that you claim mu to be equal to, you don't believe that. You actually believe the alternative hypothesis, right? So, large. Now, there's 72 different ways I can tell you don't believe the null and you believe the alternative. But if you've got a large value of your test statistic, let's see. One way to say it is I reject H0 in favor of the alternative. Translation, you don't believe the null, you believe the alternative. So when you start seeing z-scores like 2.92, 3.42, these are gigantic. And when I'm talking large test statistic, a large z-score, I don't care plus or minus. Plus or minus just tells me which way you're going. Plus means you're going to the right, minus means you're going to the left. A minus 3.25, that's a gigantic z-score to me. Okay? Yeah, the negative just means I'm going to the left. Now, if I have a small test statistic, like 0.52, 1.11, not very far away, in other words, my hand movement's exactly what's going on here. Mu, the null hypothesis says mu is equal to whatever. Out here is large. Here is you're not very far away from the center. All right? So, in terms of whether I believe the null or I believe the alternative, all I'm going to tell you here is I'm going to tell you fail to reject H0. Now, at this point here, at this beginning of these tests of significance, you never prove that the null hypothesis is true. Just because you got a small z-score, you're not very far away with your x-bar, that doesn't mean the null hypothesis is true. If we take a different sample, hell, we might get an x-bar that's far away. In other words, you're not doing this to confirm the null hypothesis. The way the test is set up is you're looking for evidence against it, against the null, and so then you have evidence in favor of the alternative. So when you have a small test statistic, you're not very far away from the center. You fail to reject H0, it's one way to say it. Okay? Another way to say it is the data look, I'm giving you X bar. Your data is coming to you in the form of this sample mean, your X bar. That's your statistic. The data, X bar, is consistent with H0 being true. I'm not telling you H0's true. I'm telling you the data is consistent with it. When you assumed H0 to be true, the data that gave me an X bar that wasn't very far away. Again, you're not proving the null hypothesis is true. It's just you can't say anything. Remember I told you on Thursday a jury trial is a test of significance, right? Remember the judge says the guy's innocent until proven guilty. And then the lawyers, they present the evidence, right? And so I got my hands moving like this last week. When I'm beyond a reasonable doubt, right? When I'm beyond this point, you come back and tell me the guy is guilty. What about when we're not that far? In other words, we're not far from, we're not beyond what a reasonable person would assume. What do we say about the guy? We say the guy is not guilty, right? Do we ever say he's innocent? No. That's this small test statistic, right? You're not very far away from him being innocent, but you're not going to tell me he's innocent. You're not going to confirm his innocence. You're going to tell me he is not guilty, right? Same thought here. Now, when we're doing a test of significance, what we're looking for is a large test statistic. We're looking for large z-scores. Why? Because now we know that we don't believe H naught, we believe the alternative. Small ones just say, well, hell, that's what we thought was true anyway. The data is consistent with what you just claimed. The next step is, look, let's put it to you like this. When you got a large test statistic and you're out here in the tail, all right, whatever X bar you got, whichever way you're going, you're looking at one-sided to the right or one-sided to the left, whichever way you're going and you got a large test statistic, you're out here like this, this outcome you're looking at is unlikely to happen by chance. Right? That's what we're meaning here. So we want to make that precise. We want to assign a probability to this whole setup here. Okay? So here comes your p-values. These p-values are probabilities. That's the rest of what's in that box right there. It says the probability computing, assuming that H naught is true. That's the thing about p-values. It's always computed assuming the null hypothesis is true. Now, I need to read the rest of it. That your test statistic, your z-score, would take a value as extreme or more extreme than it actually observed is called the p-value of the test. Now, what does it mean as extreme or more extreme? It's the area in the tail. If your X bar is to the right, the p-value is in the tail, right? As extreme or more extreme. If your X bar is to the left and you're looking to the left, your p-value is smaller than that. It's the area in the tail. Look, they say as extreme or more extreme to try to get you to think about it's the area in the tail. All right? I just can't, they don't want to say both, as large or larger if you're going this way, or as small or smaller going this way. So they say as extreme. It's the area in the tail. All right? Now, the next thing it says is this. The smaller the p-value, the stronger the evidence against H not provided by the data. So, small, strong evidence against H naught in favor of the alternative. Now, I'm going to put one more line here. Here's the part that screws students up. Large test statistics produce small p-values. Because a large test statistic means you're really far out the tail. Well, how much area is left in the tail? It will be small. So a small p-value means you were looking at a large test statistic. A small p-value means the outcome you are looking at was very unlikely to happen just by chance. Something is wrong here, and what is wrong is your null hypothesis. If you have a large p-value, not evidence against H naught. the data are consistent with H naught being true. Now, that's the same thing I wrote about a small test statistic, a small z-score. So the p-value is telling you how unlikely your outcome is. The smaller the p-value, the more unlikely it is. Look, I understand it's the more unlikely that it is, but it still happened. It still came from the data. So what has to be wrong is you've calculated this probability assuming the sampling distribution is centered wherever the mu is equal to in the null hypothesis. If you're really far out either tail, well, the problem is you're going to have a large test statistic or a small p-value. What's wrong? You're not centered here. If you're really far out this way, you must have been centered this way, right? That mu was less than that value. You can't be centered at there because this one's so unlikely to happen. It has such a small p-value. Okay? Now, here's what I want to do. I want to go back for a second, and I want to go back to our tasting. Remember we were doing the wine tasting? And I'm going to give you this as an example. What I had back there was this. Okay? I had... they gave me sigma was 1. I had n was equal to 10. Right, these are these DMS odors. This is what we started with at the beginning of this chapter. And we had x bar was 0.3. It wasn't the wine. This was the cola tasting, right, where we did before and after. We let it set, and they scored it on a sweetness scale. What I want to do is this. We'd already stated our hypotheses that the null was mu was equal to 0. Remember that the cola didn't lose sweetness after being stored for a month at high temperature. And the alternative was mu was greater than 0. They scored it higher before than they scored it after. Okay? What I would like to do is I'd like to use what I've got here to calculate your test statistic, calculate your z-score. Now, if I'm going to calculate my z-score, what I'm looking for is this. This is the normal distribution with a mean of 0 and a standard deviation 1 over the square root of 10. Remember, that was normal 0.316. Now, I'm going to underline this. That's why that's showing up there, right? The null hypothesis is telling you where that sampling distribution is centered. We got an x bar being 0.3. Now, you see this part right here? That's a one-sided test, and it's a one-sided test to the right. It's a one-sided test greater than, okay? If I want to find the p-value for this one-sided test, the alternative is telling you which way to look from your x bar. You're supposed to look to the right. The alternative is telling you which way to look. It's telling you to look to the right. Okay? So when I come down here to calculate my z-score, you take your x bar, your 0.3, you subtract off your mean of your distribution, which we have assumed to be 0 because of the null hypothesis, and we divide by our standard deviation. Now, that's nothing more than x bar minus mu sigma over the square root of n. This is the same z-score that you were using in the chapter about sampling distribution of x bar. Well, when you do that, you get a z that's equal to, what's my z, bud? Not very big. 0.95. What that's telling you is that x bar 0.3 is only 0.95 standard deviations greater than the mean. Is that very far away? In other words, is that a small z-score or is that a large one? Yeah, shit, that's small. Remember, 68% of all the samples will give you an X bar within one standard deviation. Hell, that's one of the 68%. It's less than one away. That's a small one. Are we expecting a small or a large p-value? Oh, shit, I'm expecting the large one here, right? That's a small test statistic. I'm expecting a large p-value. I'm expecting this X bar being 0.3 to be rather likely to happen by chance, right? So we come down here, and I'm numbering things for you. Sorry. There's a 4-step process in this test significance. The first one, state the hypotheses. The second one is to calculate your test statistic. And the third one is to find your p-value. So you come down here. Now, notice how I'm labeling this normal distribution. That's the standard normal one. That's where the z-scores live. That's that table in the back of the book. Mu is 0. You got a z here of 0.95. And I want this area to the right. So, you go to table, is that table A back there? Table A. The row you're going to go to is 0.9, and the column is 0.05. You're going to find the 0.9 row, the 0.05 column. You're going to read down, and you're going to read across. And it's going to give me my area here, and remember, again, the table A always tells you the area to the left. What'd you get, Marcus? 0.8289. If you want to the right, you take 1 minus 0.8289, which is, what is that? 117.1 or something like that. You're looking to the right, so you got to subtract from 1. So the bottom line is my p-value is that large or small? No. Here's the thing. You got to be careful when I ask you that question. You understand all probabilities are numbers between 0 and 1, right? So here you've got something that's going to happen 17% of the time when mu is equal to 0. Is that unlikely to happen when it happens 17% of the time? And the answer is no. This is a large p-value. Yeah, okay, so here's the way we think about this. P-values are always numbers between 0 and 1. They're probabilities. All right? When I get a p-value bigger than 0.1, I found nothing. Well, if I got something that happens more than 10% of the time, that's not what I consider to be unlikely to happen. Now, I'm looking at 0 to 0.1. The closer I get to 0, the more unlikely your outcome is, the stronger the evidence against the null hypothesis. Between 0.05 and 0.10, yeah, I got some evidence. Between 0 and 0.05, now we're talking. Right? If I got something, a p-value like 0.01, yeah. Something that happens 1% of the time, yeah, that's unlikely. Something that happens 17% of the time, that's not unlikely. Actually, that's rather likely in the big scheme of things. Right? Something that happens 17 out of 100? Oh, I want shit that happens like 1 out of 100. 2 out of 100. 1% or 2% of the time. That's small. Okay? So, number 4. Now, number 1 was state the hypotheses. Number 2 was to calculate your z-score. Number 3 was to find your p-value. Number 4 is, now you got to tell me what the hell you're going to do here. Do we want to reject the null hypothesis? Do we have evidence in favor of the alternative? Do we have strong evidence against the null, in favor of the alternative? What do we want to do here? This is a place where the data are consistent with H naught. That is, mu is equal to 0. You had a small test statistic. You had a large p-value. One more time, a p-value of 0.1711 in the big scheme of things, that is large. That is not small p-values. Okay? So the data are consistent with H naught. That is mu being 0. One other statement here. We would get a value as large or larger than x bar equals 0.3 about 17% of the time when mu is equal to 0. This part right here that I gave you, that is quoting the definition of p-value. That's just taking what we got in this problem, and I'm sticking it right in that definition on page 396. That's all that went on there. Look, I wanted to do one. I wanted to do 4 steps for you here because there's 4 steps. There's one other thing to do here. Okay? And then the other thing is we're going to give you here's the test. Here's what the hell you do. We're going to work a problem or two. All right? All the way through. All the steps. It's this. Is I'm on page 399. And look, I've given you 4 steps here. Right? Look, the first step was I stated the hypothesis. 2 was I found your test statistic. 3 is I calculated your p-value. And 4th, based off your p-value, I made a statement to you about the data is consistent with H not being true. And then I did that little direct quote of the definition of a p-value. Because you're not going to see any questions from me that are multiple choice at this point. The questions you're going to see that are multiple choice are going to be on the final. And I can't say that we're going to tell you what language we're going to use here. So I'm trying to give you all the language that I can give you that says you got a large p-value. What the hell does that mean? The data is consistent with H not being true. You failed to find evidence against H not. You failed to find evidence for the alternative. All right? Somebody remind me before we leave tonight is, you know where in D2L where I have the thoughts for test 1 and test 2? I have thoughts for tests of significance. And I've given you all the language I can think of in general terms for if you have a large p-value or you have a small p-value to try to help you manage the language here. Because, I'm telling you the same thing, and I can tell you to 72 different ways. You have to realize if you have a large p-value, the alternative is not what I'm looking at. I'm consistent with what the null is. Okay? The final step is, there's a number 5 here. It's called statistical significance. Now, this is not the first time you've seen this term. You saw it back when we were talking about experiments. We said the data from a randomized comparative experiment was statistically significant when the effect that you were seeing was so large that it couldn't be due to chance. And I told you at some point we would tell you how large needed to be before we started telling you something was statistically significant. Well, we're there. Okay? What we're going to do is this. This is like a final step. Not all problems have this step. Some of them only have the first 4. Some of them will have this last one, this final step. And this is a step to assess how much evidence against H naught is required for us to say something, our data, our observation, our sample, our X bar is statistically significant. Now, here's what we do. Okay? I'm on page 399, and what we're going to do is we're going to have a significance what's called a significance level. And that significance level is always denoted by alpha. That's the Greek letter alpha. Okay? Alpha is given in the problem. Common values of alpha are, now I'm going to give it to you in terms of percentage, and I'm going to tell you how we work with it. The 1% level, the 5% level, and sometimes maybe the 10% level. So we're looking at 0.01, 0.05, 0.10 level. This is look, the significance level is telling me how much evidence is required before I tell you that your data is statistically significant at that particular level. Translation, back to my mu equals whatever is telling you where you're centered. It's telling you how far your X bar needs to be out the tail. Right? There'll be some significance level. If you're past there, the data is statistically significant at that level. Right? So, look, when I'm talking about the 1% level, the 5% level, the 10% level, we're looking for, let's say we're talking about alpha's 5%, the 0.05 level. We want to have an X bar that occurs less than 5% of the time. In other words, has a p-value less than 0.05 for us to say that it is statistically significant. Okay? So here's what you do. I'm on page 399. It's a little box there. If your p-value is less than your significance level, then the data are statistically significant at level alpha. You always got to tell everybody what alpha you're using in the problem, because if I change your alpha, I can change whether your data is statistically significant or not. You have to tell me, yeah, I compared my p-value to this alpha. If p is less than alpha, if the p-value is less than alpha, the data are statistically significant. You are far enough out the tail to say the data is statistically significant. If your p-value is greater than or equal to your significance level, you are not far enough out the tail, so the data are not statistically significant at level alpha. And again, the significance level is in the problem. They'll tell you, do this significance level 5%. Is it significant at the 5% level, the 1%, the 10%? Look, 10% is like pretty large. Right? 5% is the standard. If we require a whole bunch of evidence, we want the 1%. Right? To get rid of the null in favor of the alternative. Now, here's the thing about this. All right? Why do I keep telling you, you got to tell me where you're working? What significance level are you working at? Why do I keep putting the level alpha in there? Here's the reason why. Let's say, just for the sake of things, that I have a p-value, and I'm going to use capital P for your p-value. It's 0.03. Right? So we went through, we did our hypotheses, we did our test statistic, we got a p-value of 0.03. What can you tell me about if alpha is equal to 0.05? Are the data significant or not there? Well, notice, if your p-value is 0.03, the significance level is 0.05, you're telling me that your p is less than your alpha, so the data are significant at this level. What about if I change your significance level? What about if we look at the 0.01 level? Are they significant there? No. Your P is bigger than alpha. Not significant. So you always have to tell everybody, what the heck am I comparing to? What was your significance level? Now, what about the problem we were doing before? Remember the one I had about the colas? What was our p-value? P was, right, X bar was 0.3. Is that significant at the 5% level? Is that significant at the 10% level? Is that significant at the 20% level? Yeah, but you're wasting your time. We're looking at 1, 5, or 10. 10% level, that don't happen very often. That's not significant at the 5% level. It's not significant at the 1% level. Not the 10% level. Not significant at alpha equals 10%. So here's the rest of my story. I would like to see p-values between 0 and 0.05. That means I got strong evidence against the null in favor of the alternative. If my p-value is going to turn out to be between 0.05 and 0.10, I'm praying that somebody's giving me a significance level. I'm praying they're giving me the 10% or the 5% so I can make a decision. Right? The data is significant or not. Because you start asking me about how strong things are between 0.05 and 0.10, not so good. So I'm praying that they gave me a significance level at that point. Bigger than 10%, bigger than 0.10 for the p-value, the data is consistent with H not being true. I'm not going to tell you anything about any strength of evidence or nothing. It's just, dudes, we wasted our time. We didn't find anything. The data is consistent with H not being true there. Okay? Now, here's the warning with a problem like this. There's nothing to calculate. It's just a comparison. Compare your p-value to your significance level. If it's smaller, the data is significant at that level. If it's bigger than or equal to, the data is not. That's it. That's the bottom line. There's no calculation. This is step number 5 if there's a significance level in the problem. And actually, if there's a significance level in the problem, step number 5 takes the place of number 4. You're not going to talk about rejecting the null or evidence against the null or evidence in favor of the alternative or any of that. You're just going to tell me whether the data are significant or not. Done. Everybody knows what the hell you're talking about. Here, that gives me something to compare to. Especially when, one more time, when I'm between 0.05 and 0.10 on the p-value, I'm praying for a significance level so that I can make a statement without having to wave my hands too much, is the thing here. All right? Now, before we do a problem from start to finish, on bottom of page 400, there are tests for a population mean. And your population mean is mu. That is your parameter. Now, on the top of page 401, test of significance, the 4-step process. Yeah, my 4 steps aren't the same 4 steps that they say. State, what's the practical question that requires a statistical test? Fine. Identify the parameters, state null and alternative hypothesis. That's number 1. And then choose the type of test that fits your situation. Look, you only know one test. Right? We're going to see other tests in the future, but you only know one test. Solve, carry out, check the conditions, SRS, normal population distribution, sigma needs to be given to you. 2, calculate the test statistic. Look, 1 is state the hypothesis. 2 is calculate the test statistic. 3 is find the p-value. And 4, conclude. Return to the practical question to describe your results in the setting. In other words, are the data consistent with H naught being true? Or did you find evidence against H naught? Did somebody give you a significance level? Are the data significant or are they not? Okay? That's my 4 steps. Now, I'm more interested in the box on the bottom of page 401. It says a z-test. The reason it's called a z-test for a population mean is because it uses a z-score as your test statistic. And you're going to me, do we know anything else other than a z-score at this point? And the answer is, give me a week, and you will. No, all you know now is z-scores. and what I showed you in that previous problem. It says draw an SRS, that's condition 1 of size n, from a normal population, that's condition number 2, that has unknown mean mu and known standard deviation sigma. That first line right there in that box, that's the 3 simple conditions for Chapter 16 and Chapter 17. To test the null hypothesis that mu has a specified value. Now, don't freak out when you read this. The null looks like this. It's always mu is equal to something. Well, we don't know. We've seen mu be 0. We've seen it be 75. We did different problems, right? Mu can change according to the problem. They just say that mu is equal to some value. And for that value, they use mu subscript. It's just a number. The problem I just did was 0. I know we stated hypothesis where mu was, I'm thinking we had one where it was 50 and things like that. Mu can change, right? But it's always, the null is always mu is equal to. It says the one sample z-test statistic. Yeah, let me add some more words to that. I got ready to say a bad word. It's a z-score. It's one sample because we're taking one sample, one SRS of size n, right? The z-test statistic. It's a z-score, right? That's your test statistic. And your z-score is calculated what I just showed you. Take your x bar, subtract off the value in the null. That's what you're assuming the mean to be. And divide by remember, the test is started, the way you start the test is you assume the null hypothesis is true. Okay? Now, it says in terms of a variable z having a standard normal, in terms of this z-score following the standard normal distribution, the p-value for a test of h0 against the alternative. Okay? Now look, you've got 3 alternatives. The first one is, it could have been a one-sided to the right. If that's the case, there sits your standard normal. There sits your z-score. The area to the right is your in other words, if I am doing a test of significance and I got a one-sided test, right? The alternative is one-sided here, and you're looking to the right. I am praying that your x bar is bigger than. In other words, I'm praying that your z-score is positive. I'm praying your z-score is to the right of the center there. If it's not, somebody screwed something up somewhere. Because you understand, if I'm looking to the right and your z-score is to the left, your p-value is bigger than 50%, right? Because it's still the area to the right. This is telling you which way to look. It's telling you to look to the right of your z-score. Another possibility is the alternative could have also been a one-sided, but you could have been to the left. Hopefully your x bar is to the left, your z-score is negative, and so the picture I should be looking at is, under the standard normal, is I should be trying to find, that should be your p-value to the left. Why to the left? That's telling you to look to the left. So with the one-sided test, the alternative is telling you which way to look to find the p-value, where to find the area. Whether it's to the left, here, the one before, to the right. Okay? Okay. We got to be careful about the two-sided. Okay? If you've got not equal to, this is a two-sided test. You know, our book talks about a two-sided alternative. You will go either direction. Now, everybody look at me for a second. You do understand there's only going to be one sample, there's going to be one x bar. It's either going to be to the right or it's going to be to the left. Agreed? Yeah, I'm not making anything drastic here. It's either going to be this way or it's going to be this way. But when you set the test up and you stated your hypotheses, you were willing to let both directions count against you. Yeah? Because you were saying, look, here's the way the tests work. It's not like you look at the data and find your x bar and then make up the hypotheses. That's not the way this shit works. You know, the hypotheses are stated. Somebody takes a sample and then you calculate your x bar. So if you've got a two-sided alternative, a two-sided test, your X bar is going to be one way or the other. It's still going to have a z-score one way or the other, but what you have to do is, since you allowed the two-sided test, you didn't know which direction to look to start with, you have to let both directions count against you. So one of two things can happen here. One, you could have gotten a positive z-score, and you find this area here. Now, I'm going to call that some probability here, because your p-value is going to be 2 times that amount. This is what you have to do, is because when you set the test up, you were willing to let both directions count against you. There's only going to be one direction. If your z-score is positive, look at the area in the tail and double it. That's how you let both sides count against you, because you were letting both sides happen here. Or, this is an or here, one of two of these are going to happen. You got a z-score that is negative. You find this area in the tail, then your p-value is going to be 2 times that. Both of these are not going to happen in the same problem, one or the other. Find the area in the tail and double it. That's how you let both sides of this two-sided test count against you. Let me ask you this. Which one requires more evidence to get rid of the null in favor of the alternative, a one-sided test or a two-sided test? Two-sided test, the one-sided test, right? Because look at it this way. The one-sided test, you're only counting one way, right? Two-sided test, you're counting better. You're going to have to be further out on the two-sided test to actually have a small p-value, because you're doubling that, because you didn't have enough information up front to make any wise decisions about your hypothesis. So a two-sided test is going to require more evidence here. Now, make a note on page 401, that little box there, because that's not the last time you're going to see that little box where it says a z-test for a population mean. It won't be a z-test for a population mean, but you see those 3 pictures there and those 3 p-values? Every time we do a test of significance, that's how you find the p-values. One-sided to the right, you look to the right. One-sided to the left, you look to the left. Two-sided test, if it's to the right, find the area, double it. If it's to the left, it's negative z-score, find the area and double it. Now, here's what I want to do. I'm looking for a problem here, and I'm on page 403. Okay? And I want to look at problem 1714. So this is a problem from scratch. We'll work from start to finish. All right? So if I look at this 1714 on page 403, it says, here are 6 measurements of the electrical conductivity of an iron rod. I got 10.08, 9.89, so on and so forth. The iron rod is supposed to have conductivity 10.1. Okay? Notice, a couple are below, 3 of them are below, 3 of them are above. It says, do the measurements give good evidence that the true conductivity is not 10.1? Now, everybody listen. Okay? I know I'm in chapter 17. This has got to be a test of significance. Let's say this shows up somewhere and they don't tell you. How do I know I'm looking at a test of significance? Does everybody see where it says, do the measurements give good evidence? What's the magic word there? The magic word is evidence. Do the data give good evidence that the true conductivity is not 10.1? Evidence tells me test of significance. You're not trying to estimate anything with a confidence interval. You're trying to do a test of significance here. Now, the rest of it says the 6 measurements are an SRS from the population of all results we would get if we kept measuring conductivity. This population has a normal distribution. Anybody know why I'm numbering here? SRS, simple condition number 1. Population distribution is normal. That's number 2. With mean equal to the true conductivity of the rod and a standard deviation 0.1. Okay, SRS, normal, population, distribution, and sigma is equal to 0.1. Condition 1, 2, 3. Now, out of these three, does anybody understand which one's the most important for us? I'm not doing shit unless somebody tells me the standard deviation. I don't care if it's an SRS. I don't care if the population distribution is normal. I can't do anything unless somebody tells me sigma at this point. Right? That's the thing about chapter 16 and 17. Every problem I've worked for you, whether it's a confidence interval or these tests of significance, sigma is always given to you in the problem. Does anybody know why I'm making a big deal about that? Give me till Thursday and next Tuesday, and I'm going to give you problems where sigma is no longer there, and we're going to do something different. So then you have to be able to decide, when do I use what? It's not like I just have one confidence interval, one test of significance. I'm using this, what we're doing here is because sigma is given to me. Okay? Now, it says, use this information to carry out the test. I'm not going to follow any four-step process. I'm going to follow my four-step process. There's the conditions are met. Okay? Step number 1 is to state the hypotheses. My template looks like this. The null is mu is equal to something. Remember, the true conductivity is this mean of all the measurements we would get. The alternative is mu. I don't know. Now, where do I find out my values here? I go back and look and see what it asked me for questions here. It said, do the measurements give good evidence that the true conductivity, that mu is not 10.1? What's it mean to be not? It didn't say greater than 10.1. It didn't say less than 10.1. It said not 10.1, means not equal to 10.1. If that's not equal to 10.1, then that is equal to 10.1. The null is mu is equal to that value. Everybody understand, you never have mu is equal to 10 and mu not equal to 11 down here. Whatever that value is stays the same for both of them. You are looking at a two-sided test here. Everybody agree? Yep, not equal to. Number 2, this is where you calculate your test statistic. You calculate your z-score. So I'm going to take my z-score. Now you notice I'm not drawing you pictures at this point. I got z is equal to, what do? I take my x bar, I subtract off my mu naught, and I divide by sigma over the square root of n. Now, where am I going to find x bar in this problem? Because you know I never did read x bar was equal to. Where am I going to find it? Did they give me the data? If they give me the data, can I calculate x bar? In other words, if I take my 10.08, 9.89, 10.05, 10.16. If I add those up and divide by 6, right, can I do this? So you're going to have to calculate x bar. X bar turns out to be, Marcus? I mean, I can make a guess at this. .08. This was calculated, don't freak out, they didn't give it to us, from the data. They gave you the data, you can calculate your x bar. Nobody's going to give you 100 pieces of data and ask you to calculate x bar on a calculator. Hell, there's 6. Okay? Let me ask you this. What's your sample size here? How many did you add together? N is equal to 6. That's everything I need to know here. If x bar had been given to me, fine. They still got to give me the sample size. So my z here is, I'm going to take your 10.08, right? Now, does everybody know what I'm going to subtract? It's the mean, right? We assume the null hypothesis is true. We're going to subtract 10.1. You're going to take your 0.1, and you're going to divide by the square root of 6. That's going to give me my test statistic. All these numbers came from the problem. X bar, we had to calculate it. Sorry. The 10.1, I'm going to circle this. We assume the null is true. That's the reason for that value being 10.1 there. The 0.1, that signal was given to me in the problem. The sample size was they told me there were 6. What we get for a z-score here, bud? Negative 0.45. It's telling me your x bar was less than the mean. Oh, it seems reasonable. Okay. Let me ask you that. Is this a large or a small one? Oh, this is small. Look, the only reason I ask you that is if all of a sudden you turn around and you get a p-value of 0.001, you screwed some shit up somewhere. Because we're expecting a large p-value here, right? Okay? So, step 3 is your p-value. Now, I will draw you the picture at this moment. Now, here's where you got to be careful. We're doing a two-sided test here, right? How do I know that? The alternative is two-sided, yes? So I need to find the area, since the z-score is negative, I need to find this area here. So you go to table A. What row am I in? I'm in the negative 0.4 row. The column is 0.05. You're going to find negative 0.4 row, the 0.05 column. You'll read across, you'll read down. You'll get some area under this curve. What'd you get? 3264. Now you notice here, I made a note to everybody that this is a two-sided test. Okay? What happens on a two-sided test here? In other words, that's not your p-value. Your p-value here is 2 times 0.3264. Remember, you had to let both directions count against you. And when you double this, you're going to get 0.6528. Is that large or small? You got an X bar here that happens 65% of the time. That's not something that's unlikely to happen. That's better than a coin flip. In other words, this one here is really, I should have said gigantic p-value. Because we can't screw this one up. It's not like I got to think about, okay, what should I say here? Are we going to get rid of the null hypothesis, or do you want to reject the null in favor of the alternative with a p-value of 0.65? Oh, no. That's huge. Okay? So, number 4, this is the conclusion. Okay? We fail to reject H0. The data are consistent with mu equals 10.1. Look, I'm trying to give you like a standard statement. And when I say a standard statement, that's my standard statement. Oh, no. I don't want to get rid of I don't want to get rid of the null in favor of the alternative. That's a gigantic p-value. The data are consistent with mu being 10.1. Again, I'm trying to give you the language. The probability of having a value as extreme or more extreme than x bar being 10.08 is 0.6528, I think. if you like, the probability of having a value as extreme or getting a value as extreme and more extreme than X bar equals 10.08 is 65%. That's gigantic. That's huge. You didn't find anything here. So, I'm trying to tell you, don't get rid of the null hypothesis here and tell me that the alternative is true. Do not tell me you got evidence for the alternative. You don't. So then we go back to the question. I mean, there was a question mark here on one of these sentences, right? Do the measurements give good evidence that the true conductivity is not 10.1? You understand? It's asking you, do the data give you evidence in favor of the alternative? What's the answer to that question? This is a yes or no. And the answer to this question is, oh, hell no. No. The data didn't give me any evidence that the true conductivity that mu was not 10.1, right? So the answer to that question is, nope. No, thank you. Okay? Now, I would like to do another one. I want to do one with this two-sided so that I can scream at you about doubling it. Okay? So, look, I know there's one more thing in this chapter here, significance from a table. I don't need it. If somebody's going to ask you about your data being statistic significant, somebody's going to give you a significance level here. All right? You don't have to worry about significance from a table. If I come over here to your homework problems, and I'm going to look at it for another one that's just start to finish. Can we look at 1730? The reason I'm picking that one is because I don't want to have to fool around with calculating X bar and all this. I'm looking at 1730. I'm trying to give you what I consider to be typical problems here for this chapter where you do a test of significance. That one about the conductivity, that's typical, right? That's a typical two-sided test. If I look at 1730, it says student study times, exercise 1619 on page 387. We did that in class for a confidence interval. Describes a class survey in which students claim to study an average of X bar equals 15.3 hours in a typical week. Regard these students as an SRS from the population of all undergraduate students at the university. Does the study give good evidence that students claim to study more than 15 hours per week? Now, I'm going to back up and I'm going to go find that problem. You know why I'm backing up? Was there anywhere they told me sigma? No. I'm going to have to back up to this page 1619, and that problem is on page 387. So I went back to page 387. We did this one in class. It says a class survey in a large class for first-year college students asked about how many hours do you study during a typical week. The mean response of the 463 students, there's your sample. The problem we're looking at now tells me it's an SRS. Gave me an X bar, which was 15.3. It says, suppose that we know that the study time followed normal distribution, normal population distribution. And that sigma is equal to 8.5. Okay? I'm going to check these. There's your conditions. They added in a simple random sample in chapter 17. Now, they didn't give me the data. They gave me the X bar. They gave me the sigma. They gave me the sample size. They told me the population distribution is normal. Hell, this problem 1730 tells me it's a simple random sample. And so it says, does the study give good evidence? What do they want? Evidence. Test of significance. Right? Give good evidence that students claim to study more than 15 hours per week on the average. Okay? Step 1, state the hypotheses. The null is mu is equal to something, and the alternative is mu. That's my template. When I'm trying to make a test of significance, do a test of significance for a population mean mu. It says, state the null and alternative hypothesis in terms of the population mean study time in hours for the population. Okay. Does the study give good evidence that students claim to study more than 15 hours per week? What's more than mean? Greater than 15. That has to be equal to 15 there. Okay? Part B, what is the value of your test statistic? The problem is leading you through my 1s and 2s. 2, your test statistic. Z, you take your X bar, 15.3, subtract off 15, take your 8.5, divided by, what was it, 463, your sample size? This is your X bar minus your mu naught, sigma over the square root of n. I'm taking that value right there, and that's what's showing up there. The test statistic, the test is done assuming the null hypothesis is true. Marcus, what did we get this time? Surely we got something positive, right? Really? Shit. Oh, no, the reason I was saying shit? It'd be nice if we got a problem here. I would have picked the problem where we all of a sudden got a large. Is that small or large? Nah, see again? That's small. So then we go to number 3. Number 3 is your p-value. Mu is equal to 0. Here sits your z of 0.76. I'm going to scroll back up. I keep going back to remind you where I'm not making shit up. This is where it comes from. The alternative is telling you to look to the right. So I want the area to the right. I'm going to table A. I'm going to the row that's 0.7, and the column is 0.06. The table always tells me to the left. What'd you get here? Something big, right? 7764. I want to the right. I'm going to take 1 minus that. Is that large or small? You got an outcome that happens. You have an outcome here that's going to happen 22% of the time, as extreme or more extreme, as large or larger than that. That's not an outcome that's unlikely to happen. It happens around a quarter of the time, quarter of the time, right? That's not unlikely. Okay? So number 4 is we fail to reject. You're going to see me write that every time you see a large p-value. There's no way, and I can't believe the test on when we do this on the final, that all of a sudden somebody's going to leave that as your answer. No, that's just my general statement here. I'm trying to get it in your head. Look, you don't want to get rid of the null. You failed to reject the null hypothesis here. Okay? So what is it? The data are consistent with mu being 15. The data is consistent with the null hypothesis being true. That's a possible answer because at least that's going back to the problem, right, in the context. We're talking about 15 hours of study time per week. And then the other one is the probability of having a value of x bar, a value as large or larger than x bar being 15.3 is 22.36%. You understand why the last two problems didn't give you a significance level? You're not even close to being significant in either one of them. The one about the true conductivity, this one about study times, hours per week, you're not even close. What do you want to compare? You want to compare that p-value being 0.2236 against 0.05? You're not significant. You want to compare it against 0.10? You're still not significant. There's not even close here. Right? You found nothing. The first problem we did tonight had 0.1711 as a p-value. This one had 0.2236. Hell, the other one had 0.65, right? Those are all large p-values there. Now, let's do another one. Yeah, I mean, I know I should move to the next chapter, but I want to do another one, and I'm going to hope the one I pick has a large test statistic and a small p-value. Okay? Let's go to 1742. Okay? I'm on page 413. It says sulfur compounds cause off odors in wines, so winemakers want to know the odor threshold, the lowest concentration of a compound that the human nose can detect. We did this somewhere recently. The odor threshold for dimethyl sulfide DMS in trained tasters is about 25 micrograms per liter of wine. The untrained noses of consumers may be less sensitive, however. Here are the DMS odor thresholds for 10 untrained tasters. Well, your sample size is 10. Now, I'm going to do it like this. I would hope that this is an SRS. It doesn't really tell us that. All right, so I put a little question mark there. It says I got a 30, a 30, a 42, 35, so on. Assume that the odor threshold for untrained noses is normally distributed. Yep. So you got a normal population distribution. That's good. And they tell me sigma is equal to 7 micrograms per liter of wine. So these are both good things. Then the question is there evidence, test of significance, that the mean threshold for untrained tasters is greater than 25? Number one, you state the hypotheses. Mu is equal. The alternative is mu something. Normally, the way these questions work, and if you'll pay attention to the ones I've already worked for you, the question is about the alternative. It wants to know if mu is greater than something, less than something, or not equal to something. Here it wants to know if mu is greater than 25. Do we have evidence for this? That mu is greater than 25, that means that has to be equal to 25. Okay? So you're a one-sided test again. Now, 2, you need to find your z-score. And your z-score has been the same every problem I have done. Now, you notice I never wrote down X bar. They gave me the data. Can we find X bar? Can we calculate X bar from the data? And the answer is yes. There's only 10 numbers here, and we got X bar to be 29.4. This was calculated from the data. Okay? So then we're just going to plug in. Our z is going to be 29.4 minus the 25. Does everybody know why I'm using the 25? I mean, I can circle again. That's the value that's in the null, right? We're making a claim where that sampling distribution is centered at 25. And then you're going to take your population standard deviation, which was 7, and divide by the square root of your sample size. You pull out a calculator, and this time we get a z of, what is it? Really? No. What's my z-score? 1.99. Ooh. Now, to me, 1.99, that's not really what I would call large, and that's not what I'd really call small. I mean, we're close to 2, right? What do you know about 2? 2, there's 95%, so there's only 5% outside of that, right? We might be close here, right? This p-value is going to be a little bit smaller, okay? So, I'm not going to tell you that's large or small. Less than 1 is small, greater than 3 is large. You start getting me between like 1.5 and 2.5, and then I have to start thinking you won't see me say large or small. Okay? 3, p-value. Standard normal. Here sets my z of 1.99. Does everybody understand why I'm going to shade to the right? It was a one-sided test. It told me mu was greater than 25 to look to the right there. Okay? So we're going to go to table A. We're going to go to the row that's 1.9, and the column is 0.09. It's going to tell me the area to the left is is that the 0.97 something? What did you say, 9767? So if I want this one, it's 1 minus 0.9767. .0 0.0233. 1.99 must be considered a large z-score. That's a small p-value, right? So here I know my p-value. My p is equal to 0.0233. Now, that's what we're looking for, right? We're looking for a small p-value. Yeah, that is a small one. It's less than 0.05. You've got something that's only going to happen 2% of the time. That's what we call unlikely to happen. Okay? So, what do you want to do here? I want to reject H naught in favor that's my general statement when I say a small p-value. Now, do we have strong evidence against the null in favor of the alternative? That is a small p-value. The closer that p-value gets to 0, the stronger the evidence is. So we have strong evidence. Against H naught in favor of, again, that's still just a standard statement. That's still like, no, I haven't used the context of the problem. We got strong evidence that that's telling you I got strong evidence that mu is greater than 25, right? I got strong evidence in favor of the alternative here. Now, I would like to go back and look at the problem, and we're looking at the, is there evidence that the mean threshold for untrained tasters is greater than 25? Well, we got strong evidence that the mean odor threshold, what the hell was it for? For untrained tasters is greater than 25. So the answer to the question is there evidence that the mean odor threshold for untrained tasters is greater than 25? Yeah, there's evidence. Strong evidence. The probability of getting a value as larger than, what was it, 29.8 or something like that? is 2.3%. That's an unlikely outcome to happen. This is the flip side of the other problems I've done. Now, the first two statements here, those are like just typical standard statements when I see a small p-value, not in the context of the problem. The third one, that's a little bit better, right? The last one, now I'm completely in the context of the problem, telling you exactly what we have. When you see a multiple choice question on the final like this, usually the answers are like the last one there, in the context of the problem. I always like to tell you whether I want to reject H naught in favor of the alternative or fail, and then we'll make whatever statement it is. I figure if I can get you to understand that, if I can get that stuck in your head, that you're looking at a large p-value, you don't want to reject the null, then you'll pick the one that says that in the context of the problem when you're reading the answers. I'm hoping. Okay? That's what I think. Like I said, because I can tell you, look, I told you the same thing 4 different ways. And the bottom line was, you got a small p-value. You had a large test statistic, you had a small p-value. You don't believe the null, you believe the alternative. Now, how in the hell you want to write that? You want to reject the null in favor of this? You got strong evidence. That's all saying the same thing to you. You understand how to take a multiple choice test? Especially on problems like this. 4 of them are on one side of the question. One of them is the correct side. If you have a small p-value, only one of them is telling you got a small p-value. The other 4, you know what the hell they're telling you? You got a large p-value. Right? It's always like that. So look, here's where we're at. I've worked 2, 3 straight. How do I know what I'm looking at? Here's what I wanted to show you before we go. All right, and then we'll pick up with chapter whatever it is on Thursday. But I'm going to make this available to you, my thoughts for test of significance. And what I tried to do for you is thoughts for test. I tried to give you all the language I could think of that help you spit out. Look, you can't have any problem stating a hypothesis. That just comes from the problem. You're supposed to already know how to calculate the test statistic and the p-value. Now it's the interpretation of the p-value. What do you want to do about your test? This is the language I'm giving you here. If you have a large test statistic, a z-score, and a small p-value, they go hand in hand. A large test statistic can be either negative or positive. The sign is just telling you the direction the x bar is for the mean. I'm telling you exactly what to say. The closer you get to 0, the stronger the evidence against the null, so on and so forth. Bottom line, I wrote notes and I bottom lined your ass. Here's what I'm trying to tell you. You get a large test statistic and a small p-value. Bottom line is, you do not believe the null hypothesis, we believe the alternative. Now, how do you want to say it? I gave you 3 possible ways to say it. Okay? If you have a small test statistic, a z-score, a large p-value, and again, I told you the same thing, I bottom lined you here. Is that the test is set up for look evidence against H naught, and you did not find enough evidence to reject H naught. The data is consistent with it, right? That's the bottom line. And I also I reminded you about your statistical significance, if that's in the problem. If it's in the problem, they'll say, are the data statistically significant at this alpha level, right? 5%, 1%, 10%. You just compare. That takes a lot of language off of us. I would pray for somebody to always tell me, look, the significance level is 5%. Just compare your p-value. It don't get any better than that. It don't get any straightforwarder than that. I should go back and change where the definition of p-value is on page 242, because that was from before we changed books. It's on page 396. If I can remember when I go upstairs, I'll change that to 396. If not, when you look on page 242, you'll be wondering what the hell I said. It's on page 396. All right? On Thursday, we're going to pick up with the next chapter. It's about inference and practice. It's the things to be aware of. It's about a half-hour talk. And then we're going to skip a couple chapters and go to proportions. Everybody be careful going to the house. We'll see you on Thursday.